Hello students, welcome back to the lecture. In the last lecture we discussed about electronic spectra of diatomic molecule. We looked at how to get the different terms for a diatomic molecule. I will continue with that and then I will go to discuss spectra of transition metal complexes. So, as I discussed in the last lecture, terms for diatomic molecule is determined by angular momentum around the internuclear axis. It is not determined by orbital angular momentum, it is determined by angular momentum around the internuclear axis, and that is denoted by lambda. Lambda is analogous to ml in atoms. For example, a p orbital has L is equal to 1, ml is equal to 0 plus minus 1. Electronic terms are named based on their overall angular momentum on the internuclear axis. So, what we need to do first is to get the overall angular momentum, and the way we calculate angular momentum is angular momentum on the internuclear axis. Lambda is equal to sigma over I for lambda I. What does that mean is it is simply sum of lambda 1 plus lambda 2 plus lambda 3. If lambda is equal to 0, that corresponds to sigma term. When lambda is equal to plus minus 1, that corresponds to pi term, and when lambda is plus minus 2, that will corresponds to delta term. This already I have discussed in the last lecture. Today I will discuss first about symmetry, because it is also very important to know symmetry of the molecular orbital which is generated due to mixing of two atomic orbitals. Symmetry is particularly important if we want to look at the selection rule. For homonuclear diatomic molecule or symmetric linear molecule, for example CO2, it is convenient to label molecular orbitals and terms according to symmetry G and U. G stands for Gerade and U stands for ungerade. This is the symmetry with respect to inversion through the center of symmetry. So, ungerade U stands for anti-symmetry with respect to inversion through the center of symmetry, whereas gerade stands for symmetric symmetry with respect to inversion through the center of symmetry. For example, here you see that suppose sigma orbital is formed. Sigma orbital can be of two types, when both lobes has positive charge, when one lobe has positive charge, another negative charge. So, when both lobes has positive charge, and if you take center of inversion, then what you are going to see is that it is symmetric with respect to center inversion, and that is why this is labeled G. Whereas, in this case this is anti-symmetric with respect to this center of inversion, and that is why this is anti-symmetric, that is why it is labeled U. U stands for ungerade and G stands for gerade. What generally is observed is bonding sigma orbitals and anti-bonding pi orbitals are always gerade, whereas anti-bonding sigma and bonding pi are always ungerade. So, this look at this is your anti-bonding sigma, this is your anti-bonding sigma orbital and that is ungerade, whereas this is bonding sigma orbital and this is your gerade. So, suppose we take the case of S2, where 1s orbital combine with 1s of the second hydrogen and gives you two orbitals, one with positive and one is positive and negative. lobes. This is your anti-bonding and this is bonding orbital. And as I told you that this will have label u and this is going to have sigma, and you have two different molecular orbital, one is known as 1 sigma g and another is known as 1 sigma u. Now, consider the overlap of p orbital. There can be head on overlap. If there is head on overlap, what you will get is this orbital, which is sigma molecular orbital. Look at the center and look at the inversion, then what you will find is this is symmetric, and that is why this is Gerade G. Whereas, if there is anti-bonding orbital formation, then it will not be symmetric with respect to center of inversion, and that is why this is ungerade U. This is sigma star molecular orbital. So, whether sigma orbital forms from overlap of s orbital or p orbital, the bonding sigma orbitals are always Gerade, whereas anti-bonding orbitals are always ungerade, and that is what we have written. Bonding sigma orbitals are always Gerade, whereas anti-bonding sigma orbitals are always ungerade. Now, look at sideways overlap of p orbital. If there is sideways overlap, then this is the your bonding orbital, molecular orbital, and this is your anti-bonding orbital, So, this is the molecular orbital formed by the sideways overlap of p atomic orbitals, and you are getting bonding orbital and anti-bonding orbital. So, if you take the center inversion here, then you can see that here is blue, then here is red, and so this molecule is anti-symmetric with respect to your center inversion, and that is why it is given U symbol ungerade. Whereas, if you look at anti-bonding, then you see here this and this lobe is same, this lobe and this lobe is. So, it is symmetric with respect to center inversion, and that is why your pi anti-bonding orbitals are Gerade, whereas pi bonding orbitals are ungerade. So, now look at the picture of molecular orbital picture of fluorine, and this is the way your electron has been filled. Now, you see here if 2s combines, it gives you bonding, one bonding orbital, one anti-bonding. Bonding will always be Gerade and anti-bonding is ungerade. Sigma, so if 3p orbital of 2p and 3p orbitals of another f combines, they will give one sigma and sigma anti-bonding orbitals, and you can look at this is your pi bonding and this is your pi anti-bonding orbital. And as I told you that this will be Gerade, this will be ungerade, whereas pi bonding orbitals are ungerade, whereas pi anti-bonding orbitals are Gerade. So, this is your molecular orbital picture of F2. There is another kind of symmetry which is known as reflection symmetry. Reflection determines if a given orbital is symmetric or anti-symmetric upon reflection through a plane that contain both nucleus. So, when an orbital is symmetric, it is labeled plus, when an orbital is anti-symmetric, it is labeled minus. So, you can see this is your overlap, which is sideways overlap between two p orbital, and if you take a nodal plane containing both nucleus, what you are seeing is plus, here is minus, and so it is anti-symmetric with respect to reflection, and in that case you label it as negative. One thing you need to keep in mind that reflection only applies to sigma states. For lambda is greater than 0, there are no reflection levels, no reflection levels. So, here I have written configuration and terms, different terms. So, if there is sigma 2, then you will get 1 sigma plus, okay, 1 sigma plus. So, this is your lambda, this is your symmetry with respect to reflection plane. Similarly, for pi 2 you can write different term, for pi 3, pi 4, and there are different kind of configuration and corresponding term. Now, let us go again discuss a molecule, for example, lithium 2. What will the ground state? This is the ground state. There are 2 electron in 1 sigma g, 2 electron in 1 sigma u star, and 2 electron in 2 sigma g. Their cells are all closed. Their cells are all closed, and since all cells are closed, it means symbol of ground state of lithium 2 plus is 1 sigma g, 1 sigma g. If you take excited state of lithium 2 plus, let us take 1 electron and jump it to 2 sigma u star. So, now 1 electron is in 2 sigma g and 1 electron is in 2 sigma u star. Since both electron in the open cell has m is equal to 0, this corresponds to m is equal to 0, this corresponds to m is equal to 0. So, lambda will be 0, but two value of S is possible, one like this and another like this. So, S is equal to 1 is possible, S is equal to 0 is possible, and so you have a term from S is equal to 0, multiplicity will be 1, S is equal to 1, multiplicity will be 3. So, 1 and 3, and you have ungerade at the parity, that is also known as parity. Now, let us think about some other molecule. For example, let us calculate what will be the term for N2 ground state. So, this is your N2 ground state and the electronic configuration. So, 2 in sigma g, 2 in sigma u, 4 in pi u and 2 in pi g. So, you can see this is 2, 2, here there are 4 and there is 2 electron in this sigma g. So, you can see 6 plus 4, 10, 10 electrons is filled here, and certainly there are 4 electron in 1s orbitals. So, we have just removed 1s orbital, and so you have this distribution of electron in molecular orbital. Now, you look at here, the 2 electrons are in sigma, and so lambda is 0, and S is equal to 0 because they need to be paired, and so what you get is 1 sigma g plus, 1 sigma g plus. Sigma, remember sigma bonding orbital is always Garade. Now, let us talk about NO molecule, and let us write ground state term for it. So, in NO what will happen? 2 electrons here, 2 electrons here, 2 electron in 2 p sigma, 4 electron in 2 p pi and 1 electron in 2 p pi star. Since it is a non-symmetrical molecule, and so there is no Gu symmetry here. Now, look at this part, you have 1 electron in 2 pi star, and that means lambda is plus minus 1, and therefore, there will be a pi term, and since there is 1 electron in the open cell, and so S is half, and so multiplicity will be half into 2 plus 1 is equal to 2. So, that will give rise to 2 pi state. this will give rise to 2 pi state. We can look at the oxygen ground state. In oxygen, again 2 electron in 1 sigma g, 2 electron in 1 sigma u, 2 electron in 2 sigma g, and 4 electron in this pi u, and 2 electron in your pi g. So, this is the way you have electrons distribution in different molecular orbitals. So, here lambda will be 0 or plus minus 2, lambda will be 0 or plus minus 2, and S will be 0 or 1, and 2 electrons has G into G. So, G all term is Garade, and so you will have all these 6 different states, but this neglects Pauli principle, and these 3 terms violates Pauli principle, and so they do not exist. What exists is these 3 terms, what exists is these 3 terms, in which triplet state is lowest. So, this one will be lowest. Now, let us look at the spectra of O2 molecule. We have already decided about, we have already looked at the term symbol for O2, and we have also looked at the term symbol for oxygen. So, if you look at the term symbol for your oxygen molecule, there are 3 out of this. This one is the ground state, and that is what is shown. Okay. So, 3 sigma minus G is the ground state, and out of this, since lambda is greater here, so this will be lower in energy in comparison to 1 sigma G plus. So, this is for oxygen molecule, and now if you go up, this oxygen molecule at this position dissociate into oxygen atoms, and if you remember the terms for oxygen atom, these 3 terms are for oxygen atom, in which 3 p is the lowest in energy, and that is what is shown here. After that, there is 1 d, which is shown here. So, here the dissociation of O2 molecule is taking place between 2 oxygen in 3 p state, whereas in this oxygen is breaking in 3 p state and 1 d state. So, this is the spectra of oxygen. This is the way you can explain the electronic spectra of diatomic molecules. Now, the selection rule. So, according to selection rule, you have the rule 1 says that delta lambda should be equal to 0 or plus minus 1, then only your electronic transition is allowed. For example, sigma to sigma, pi to sigma, delta to sigma transition are allowed, but not delta to sigma, because you remember for this lambda is 0 and for this lambda is 2. So, difference is minus 2. So, this is not allowed. So, please keep this in mind. The second is rule is delta S is equal to 0. So, what does that mean is triplet to triplet transition is allowed, singlet to singlet is allowed, not triplet to singlet or singlet to triplet. So, this is very important selection rule. A triplet to singlet transition are strictly forbidden. Triplet to singlet transitions are strictly forbidden. Only triplet to triplet or singlet to singlet is allowed. Now, let us talk about LS coupling in diatomic molecule. This I have discussed in the previous lecture. So, what I told you that component of total angular momentum along the internucleus axis is this sign into H cross, where the quantum number this is given by vector sum of lambda plus sigma, lambda plus sigma. So, if lambda is 1 and sigma is 1 0 minus 1, then 3 pi is going to have 3 different component. This is equivalent to j, and that comes because of your LS kind of coupling. So, here basically the component of L along the internuclear axis combines with component of spin along the internucleus axis to give you this thing. And the way we did earlier for atoms, this is your lambda, this is your multiplicity 2s plus 1, and this is your this LS coupling. And now 3 multiplets can be given these 3 terms. Now, what is the electronic selection rule for these multiplets? Delta sigma should be 0 and delta this coupling parameter should be equal to 0 or plus minus. So, not only that, we also have a rule based on symmetry. What is that rule? That plus to minus is not allowed. So, this is not allowed, whereas plus to plus and minus to minus is allowed. So, since plus and minus is only relevant for sigma sigma transition, so sigma plus to sigma plus and sigma minus to sigma minus transition are allowed. The other selection rule is, this is same about how to label plus or minus. So, I will just skip this. The second selection rule, which is known as Laporte rule, is also based on symmetry with respect to inversion center. What does it says is G to U is allowed, G to G is not allowed, and U to U is not allowed. U to U is not allowed. What does that mean is sigma G plus, this is not allowed because G to G is not allowed, only G to U is allowed. So, this is not allowed, this is not allowed, but this is allowed and this is allowed. So, these transitions are allowed, and already I have explained you what does it mean by G and U. So, I will just move ahead. So, this is about a spectra of molecules. Now, I will discuss about electronic spectra of transition metal complexes. So, first question is, are DD transitions are allowed or forbidden? So, if you have studied in organic chemistry, you must be knowing that color of the your transition metal complexes are mostly due to DD transition. Sometimes it also happens due to charge transfer. So, whether DD transition are allowed or forbidden transition. So, if you remember the selection rule, what you will find that it is forbidden, transition. However, bonds in transition metal complexes are not rigid, but undergo vibration that may temporarily change the symmetry. For example, octahedral complex vibrate in such a way that inversion symmetry is lost momentarily, and this phenomenon is called vibronic coupling. And so, because of vibration coupling, DD transitions are allowed. Tetrahedral transition metal complexes are strongly colored than the octahedral complexes of the same metal and oxidation state, and bonding in tetrahedral can be explained based on sp3 hybridized orbital, and they are not pure d orbital, hence DD transition is allowed. In fact, in octahedral also there are mixing of hybridized orbital, and so your DD transition is allowed. Spin orbit coupling is likely to contribute to transition between ground state to the excited state with different multiplicity. Okay. So, let us go ahead and see what are the different term symbols. So, first we will look at term symbols for free gaseous ions, and then we will see how this term symbol changes or term symbol split when it is approached by a ligand. So, for constructing term symbol, for any d n configuration, electrons are distributed in an orbital that in a way that we obtain maximum spin multiplicity, and for any d n configuration, electrons need to be filled in such a way that we obtain large ml value, provided the electron should not be paired until all the available degenerate orbitals are filled with one electron. And this is the simple things which you must have studied in the 12th class. So, I am not going to discuss it. This already I have discussed, the term symbol for any ion or atom can be written like this: SLJ, where L is your term and J is your spin orbit coupling and S is your multiplicity. S is spin multiplicity. And for L is equal to 0, we have S state, L is equal to 1, we have P state, L is equal to 2, we have D state, L is equal to 3, that is F state. This already I have discussed when I was discussing the terms for different electronic configuration. Now, look at here, if L is 0 and S is 0, then we will get 1 S term, L is 0 half, then we will get 2 S term, if 1, 1, 3 P term, when I get 2, 3 by 2, then we have 4 D term, when we have 3 as L and 2 as S, then we get 5 F term. So, this we have already discussed, so I am not going to discuss in detail. Let us think of that if I have a gaseous ion with D3 configuration. So, first thing you need to know or do is sketch the energy levels showing the d electron. So, let us make d the orbitals, there are 5 orbitals and then you put the electrons. Now, we know what will be the spin multiplicity, this is the number of electron plus 1, that is 4. Now, let us get what is the maximum possible value of ml. So, maximum possible value will be 2, 1, 0, and so your L will be equal to 3, 2 plus 1 plus 0 is equal to 3. Remember, 0 corresponds to S, 1 corresponds to P, 2 corresponds to D and 3 corresponds to F. So, you have a F term and your spin multiplicity is 4, and so ground state for D3 configuration is 4F. Similarly, you can calculate for D2 configuration. D2 configuration, you see one electron is here, another electron is here. So, 2s plus 1 will be 3, L maximum value of L will be 2 plus 1 3, and that corresponds to F, this corresponds to F, 0 corresponds to S, 1 corresponds to P, 2 corresponds to D, 3 corresponds to F, and multiplicity is 3. So, for D2 configuration, ground state is 3F. And if you remember, we did calculated the terms for equivalent electrons, and in that case I had shown you that these are the different term symbols, in which 3F will be the ground state, because it has highest multiplicity and highest L value, and 3P will be the second one. And this table I have shown earlier in my lectures. For P2 these are the terms, for P3 these are the terms, and you see this is for different D configurations. So, D2, D3, D4, D5, and that is what I was discussing earlier. So, till now we discussed about metal ion. Now, let us look at what happens to different energy levels when a ligand approaches the transition matter. So, as expected they will split and now again we are going to the write different terms, and the terms are basically given by what is known as irreducible representation. Irreducible representation. So, right now I am not going to discuss what is irreducible representation. I will give a slight idea, so you can understand what we are trying to explain. If I have time during this course, I will take group theory. I will devote one class to group theory, so that you understand what are the irreducible representations. But what we generally do is, we look at the symmetry operation and see whether they are symmetric or anti-symmetric. For example, let us take s orbital. You have to see you have to do these symmetry operations and look at whether it is symmetric or anti-symmetry with respect to that operation. For example, if you take a rotation, you see here you do rotation, what will happen to s orbital? It will remain same, its symmetry will be conserved, its symmetry will not change. So, the s orbitals are called symmetric with respect to rotation symmetry operation, and for rotation we show them with the symbol A if it is symmetric and B if it is antisymmetric. For example, if you look at here, it is symmetric with respect to rotation, and so it has been given the name A, whereas p orbital, it is not symmetric with respect to rotation. So, if you rotate, plus will come here, minus will go up, and so it is no longer same. So, with respect to rotation, p orbital is not symmetric, and that is why it will be given the name B. Now, the second symmetry operation is reflection, and that is through plane of symmetry. So, let us pass plane of symmetry, again this looks symmetric, and so it will be given name 1. So, if your orbital is symmetric with respect to reflection, that will be given the name 1, and if it is antisymmetric, then it will be given name 2. And already I have discussed about Gerade, ungerade, so I am not going to discuss that. These terms are given based on the symmetry operation. So, s orbitals has the representation A1g, whereas p orbital has representation B2u. So, let us discuss what will be the irreducible representation for different orbitals. S we have already looked at A1g, and this will be given in the tetrahedral field, and tetrahedral complexes there will be no G and U term, and so this will have the representation given by your A1 symbol, A1 symbol. For px orbital, it will be T2, and this is T1u. In octahedral complexes, you have T1u. For py, this will be T1u, pz, T1u. So, if you look at this, these all are same, and that is why it is given the triplet name. So, it is triplet degenerate. So, px, py, pz is triply degenerate, and so it will be given T name. Similarly, here T2. Okay. For dz square, Eg, dxz, T2g, dyz, T2g, dxy, T2g. So, these three are degenerate, and so it has been given T2g name, whereas dz square and dxy is your doubly degenerate, and it has been given name Eg. So, this is the way you get the different term symbols for different orbitals. I will discuss this in much detail later on if I get the time. So, here are different terms and they are irreducible representations. Irreducible representations. As I told you, S will give you A1G, P will give T1G, D will give EG plus T2G. If you go back, you see S will give A1G, P x P y P Z will give T1U and D will give 2 EG and T2G. This is in octahedral field. So, what we are looking at is splitting of free ion terms in octahedral symmetry, and these are the different energy states which we will get when the ions are in octahedral field. Now, once we know that, it is quite easy to understand the spectra of transition metal complexes. So, first we will discuss what happens when a metal with D2 configuration is in octahedral field. Octahedral field. So, D2 configuration has these 5 terms, that is what we discussed. Now, we have also looked at what are the symmetric representation which we get in presence of octahedral field. For example, 3F will get 3 A2G, 3 T1G, 3 T2G. For you remember 1S 1 A1G, 3P 3 T1G and 1D. So, these are the different terms we get from these terms, which are the terms when ligand is not present. So, these are the terms when ligand is not present and they will split into different levels when your ligand approaches in an octahedral field, Okay. So, now first thing we will discuss correlation diagram. Correlation diagram, you see this side is the term which is there for free gaseous ion, free gaseous metal ions. So, this is for D2, again we are looking for D2, 3F, 1D, 3P, 1G, 1S, and here what we are written is, this is the way your electrons will be filled. So, 2 electrons are in T2G, in the ground state 2 electrons are in T2G. If you remember, these are the D electrons in octahedral field is filled in this way. So, this is T2G and this is EG. So, this is your ground state term, and if you take this one to, then you have a T2G1, EG1. So, this is first excited state. When both electrons goes up, then you have the second excited state. So, the term arising from free ion LS coupling should be shown in far left. The terms arises due to ligand field, that is a strong field, should be shown on the far right. That is what we showed. And now, we apply the selection rule. The selection rule is the transition are allowed between states terms with the same spin multiplicity, So, this is your terms when it is not in octahedral field, but these are the terms when it is in octahedral field, And now, look at this. What now we are going to do in this is, let us see. So, what are the terms here? 3 A2G, 1 T2G, 1 T2G. So, what we are going to do is, in this we are only going to take your the triplet terms. You see, these all are triplet terms and this is your triplet. These are not triplets. So, I am not going to consider this. These are not triplet. I am not going to consider this. These are not triplet. So, we are not going to consider it. And now, look at here. So, this is 3 T1G to 3 T1G, this is 3 T2G and this. So, now the transition can happen between terms of same multiplicity. So, it can happen from 3 T 1 G to 3 T 2 G. So, this is what you see in UV visible spectrum of vanadium S2O6 3 plus, which has D2 configuration, The second one you can look at is 3 T 1 G to 3 T 1 G, this one. And the third one which you are going to see is from 3 T 1 G to this is 3 A 2 G, 3 T 1 G to 3 A 2 G. This is basically obscured by the charge transfer transition, which I am not going to discuss in this class, but you expect 3 different peaks in the spectrum of this transition metal complex. Since only transition between same multiplicity is allowed, and as we looked at, only there are only 3 different terms with the multiplicity 3, Okay. Now, let us look at correlation diagram for D8. So, for D8 again 3F is the ground state and 3Ag will be the ground state term. In place ground state term when your ligand approaches in octahedral field, The other excited state are 3p, 1g, 1s, 1d. We have discussed this. We have told that D2 and D8 configuration has similar kind of the term, and so D8 ion is going to be of going to have same term as D8. Only difference is that when there is splitting in presence of octahedral field, this one is going to be ground state and this one is going to be highest in the energy. So, triplet, so lambda so this is A T is going to be lowest, but when you go into D8 terms will be same, only the energy order of different terms will be different. So, D2 and D8 ion is expected to show same number of transition. However, the correlation diagram of D8 is the inverse of D2 configuration, because the different terms have different energies, Now, 3 A to G is lowest in energy, whereas 3 A to G will highest in energy for D2 configuration. So, comparison of Dn and D10 minus n ion can be done. The D1 is going to have inverse correlation with D9, D2 is going to have inverse relationship with D8, D3 is going to have inverse relationship with D7, D4 is going to have inverse relationship with D6. Now, comparison of D2 ion octahedral geometry versus tetrahedral geometry. Now, again if you take D2, this was the case in D2 tetrahedral, this is D2 in octahedral, D2 in tetrahedral will be similar like D8, it will be similar like D8. So, D2 and D8 is expected to show same number of transition, but the correlation diagram of D2 octahedral is in inverse relationship with the tetrahedral geometry, and that is a bit expected, because if you remember, this is the way the d orbital is split in presence of octahedral field, whereas in tetrahedral field is down and T2 is up. and that is why we are getting kind of inverse relationship. So, it is because of approach of ligand to the ion. Now, there is another diagram called Orgel diagram, and in Orgel diagram what we do is you plot different terms as a function of delta as a function of delta. This side is for octahedral and this is for tetrahedral, and you look at this. Here you have D2 D7 tetrahedral, D3 D8 octahedral, D2 D7 octahedral, D3 D8 tetrahedral, and they have D2 T2 T1 T1, and now here you see this is A2 T1 T2 T1. So, it is just opposite, So, it changes with the delta in this way, and this is known as Orgel diagram. So, this is you see this is F term, and if you remember F term, here you see this is D2 octahedral. So, T1 T2 A2, that is what is written, T1 T2 A2, this is in tetrahedral and this is in octahedral. So, D2 tetrahedral is here, okay, for this term F term, and P always goes into 1. So, this is for T. So, in one diagram you can show what happens to the F term when you are in tetrahedral field and when you are in octahedral field. So, Orgel diagram considers only the terms with the same spin multiplicity. So, if you remember, these are with the same spin multiplicity, and that is what we are looking at, same spin multiplicity. These things is only shown here. So, D2 tetrahedral will be similar to D2 tetrahedral is same as D8 octahedral, D2 octahedral is same as D8 tetrahedral. Okay. There is another important thing to understand is basically what is known as a no crossing rule. What happens that if there are suppose 2 4 T1, this thing 4 T1, this is 4 T1, there are two terms, one is due to F, another is due to P. So, what will happen that they will not cross each other, and what will happen is it will deviate, this will go up and this will go down. So, if you look at here, this is now deviating to up and this is going down, and that is known as no crossing rule. Now, third diagram to explain this DD transition is Tanabo-Sugane diagram, and it is quite similar to the Orgel diagram. What generally we do is we plot E by B versus delta naught by B, where delta naught by B is octahedral ligand field splitting, B is your Raka parameter, and E by B is energy above the ground state, energy of excited state above the ground state. And again, if you remember, 3F goes to 3 different terms, 3 T1G, 3 T2G and 3 A2G, and this is if I increase the field and it goes up. 1D will go into 2, now you see this is 1S will go into 1, and this 3 is shown in the bold because they have similar multiplicity. You see here multiplicity is 3, multiplicity is 3, multiplicity is 3. And so, now we can look at the spectrum. So, this is the spin allowed transition of D2 ion, and you see from the ground state transition can take place to this one 3 T2G. So, 3 T1G to 3 T2G, 3 T1G to 3 T1GP, and 3 T1GF to 3 A2G. So, this is the way you can describe the spectrum, and this already I have discussed with you, and This is well known Tanabe-Sugano diagram for D2 ion. Spin allowed transition in D2, again if you look at here, if we remove all other singlet to singlet terms, then you are left with these 3 triplet terms, and here you see there is a crossing. So, that is allowed because this is between T and A, but if you go to D3, then there are 2 T terms, and now you can see it deviates, it does not crosses, it deviates, this one goes up and this one goes down, and that is again known as no crossing rule. Similarly, we can talk about spin allowed transition in D4 and D5, and it is quite similar. I am not going to discuss it, but now you can understand how to get electronic spectra, how to analyze electronic spectra of transition metal complexes. So, I will stop here. Thank you very much for listening. See you in the next lecture. Bye.